The art of portable and reusable UVM shared system memory model verification methodology across multiple verification platforms. Okay. Abstract. The shared system memory is an essential design element of IP or SoC. So the shared system memory model (SMM) becomes really important and indispensable to ensure the verification quality. So different teams or groups will deploy the different SMM per different requirements using different languages. In addition, SMM is used to multiple verification platforms such as the UVM IP standard, the UVM combo whacker, UVM CW, a kind of AMD-specific subsystem verification. So the virtual FPGA, VFPGA, a kind of simulation environment using the FPGA, nellist and glue logics. So the SoC full chip. With more verification IP, VIP's integration in verification, and a question regarding how to make in-house SMM and VIP built-in SMM work together is raised. All of these will introduce big rules, reuse challenges in AMD Southbridge Group, a portable and reusable SMM verification methodology which had been qualified across different verification platforms in multiple projects for 3 years. It really shifted left and our project schedule with low maintenance and integration effort and approximated 69% effort reduction and high verification quality. And in this paper, we will present our successful story and a solution experience for anyone wishing to take a similar approach. Keyword UVM, system memory model SMM, IP standalone as combo whacker CW, and virtual FPGA VFPGA. Section 1, Introduction. The shared system memory is an essential design element in both IP and SoC. A comprehensive system memory model SMM is crucial to simplify the design verification process while to ensure the quality. In different verification platforms, SMM is used to create test sequences, predictor, and scoreboard, and etc., with more and more companies adopting the UVM methodology to develop their verification environment from IP level to SoC. The maximum reusability is always the goal when trying to make vertical or horizontal reuse of verification environment across IP, SoC, teams, and projects. SMM reusability can be great challenges. Different verification teams or groups deploy and adopt different SMM written by different languages such as Verilog and VHDL, and System Verilog, Vera or C++ and C. It's really difficult to make different SMM works together in a specific verification platform. Only few SMM implemented the memory allocation features. Example, you can allocate exclusive regions. And potential PLI, DPI usage will affect verification performance too much. The different third-party UVM BIP provide the slave responder with different built-in SMM implementation. The legacy SMM could not easily work with the UVM memory front door operation APIs. The flexible debug capability and the specific errors injection are all required. So the generic UVM SMM deployed by the AMD Southbridge Group addresses all the above concerns. In this paper, this portable and reusable UVM SMM is presented. It can be reused without any changes across various verification platforms such as IP standalone, UVM CW, virtual FPGA, and SoC full chip. It also had been qualified in multiple successful projects for more than 3 years. In today's fast-paced semiconductor industry, in order to accelerate the verification process, lots of third-party UVM verification IPs, VIP, are integrated to reduce verification effort while maintaining the quality. However, different VIP implies different interface protocols, so this proposed SMM is also protocol independent to all required UVM VIPs. So with our successful story and and solution experience, this paper can benefit you a lot. Firstly, it attempted to discuss this sector, the idea of each key component with the big picture in a typical UVM environment, and try to explain how it works via answering several potential questions. Section 3 depicts the portable solutions across different verification platforms. Section 4 presents the debug capability for quick bug hunting. Section 5 summarizes our successful story in project and future extension. Finally, this paper concludes in section 6 by sharing that we benefit from this verification methodology. Section 2. Portable and reusable UVM system memory model verification methodology. The Figure 1. Big picture of key component in typical UVM environment. The portable and reusable UVM system memory model verification methodology is made of the 5 key concepts. UVM shared system memory export to SSMM, UVM generic save restore memory model GMEM, UVM unique slave memory sequence USM-SCQ, and the UVM memory nodes container MKC, and the UVM memory export adapter MEA. And so in figure 1, it presented the SSMM MEA, MKC, and GMEM are created in the UVM test layer. The unique SSMM reference is residing in the UVM sequences and components, such as scoreboard and predictor. The EMA and MKC also have reference in SSMM. In the next section, we will present the details of each. Before we convey the details, it is necessary to understand a few prerequisites first. The prerequisite, the system memory address alignment. The data and address alignment concept are described well in the computer architecture knowledge. In this paper, let's make AMBA bus protocol as an example. And the AMBA memory address could be aligned and unaligned when you want to access the data size bigger than byte. The word aligned address requires the address to be 0. When we allocate the data buffer, it's usually expected to return the aligned starting the address for designers to easily implement. This methodology predefined several assignment types for memory allocation. Table 1, information non-alignment in AMBA protocol. The system memory segment. In a complex SoC design, it's usually defined several different types of memory attached on the system bus. They are shared with most of IPs and play different roles per different production application requirements. On verification point of view, we can mark every type of memory as a unique memory segment which has the exclusive predefined address range. The secure related verification is become really important for Internet of Things IoT production to meet the ARM trust zone concept. Memory segment could be defined as a secure or a non-secure domain as well. The figure 2 presents a clear picture of the relationship between the system memory and the memory segments. In the IP level verification, it usually uses a good memory segment to achieve the whole memory map for verification. Improper memory setting may introduce reuse problems from IP to SoC vertical reuse. Because IP has specific accessible memory space which may cover multiple segments in SoC. It's better for IP level verification to set the exact accessible memory segment defined in SoC memory map per project. Figure 2. Concept of memory segment in an SoC. The B. UVM generic save and restore memory model. The GMEM is a system variable class can provide a singleton instance. It's designed to save and restore memory data with addresses as index. It also provides necessary protected backdoor access APIs for SSMM uses, not for end users, and DPI functions to support the legacy and VFEJ verification platform. C. UVM shared system memory expert. The SSMM is a system variable class and can provide a singleton instance. It is designed as an expert proxy to provide multiple friendly, easy-to-use APIs for end users to communicate. GMEM. It's built in the base test layers, and its reference will be passed down through the hierarchy verification environment. So the verification engineers can use it to create random sequences, predictor, and scoreboard, and etc. So current SSMM can support a set of key features as below. The built-in shared dynamic memory allocate manager, which adopted the UVM MAM concept. It helps to allocate exclusive memory region and is better for users to deallocate their region when it's useless. At the report underscore phase of test, it will free or allocate the regions automatically. User-defined memory segment with more attributes such as segment, name, base address, and access type, size, secure type, and etc. User-defined memory allocation policy to control the starting address alignment. Built-in memory adapter library to support different health protocols. Industrial standard protocols such as an in-house bus protocol, APB, AHB, AXI4, and PCIe, and etc. The backdoor access to the memory model, GMEM or the Reusable and VHDL legacy memory model. The front-door access using built-in abstract UVM MEM model. The comprehensive error injection mechanism. Multiple outstanding requests with timeout control and out-of-order transaction completion. So the responses items, post or non-post control. Response latency and burst response delay control. So data audit for a memory domain or secure check and nice debug utilities. And functional coverages. D. UVM unique slave memory sequence. USMSEQ is a unique parameterized UVM sequence which is protocol independent and designed to co-work with SSMM to support DMA traffic. The unique means it could execute on any slave UVM VIP's sequencer without any change. This sequence could be vertically and horizontally reused. It could not only support different response type from request type, but also support the same types of them. So for example, they use the response with the request type to ease driver implementation in VIP. It has a local mailbox to get the request broadcasted from a monitor and a SSMM reference to handle advanced features such as multiple standing requests, errors injection, and response control with legacy, and etc. E. UVM memory nodes container. MKC is an UVM object that has types of local associate arrays to support node layer control. For example, it supports outstanding and responses latency nodes. The nodes can control constraint by refining the weights. MKC is built in base test layer and its referent is passed down to hierarchical environment. The nodes are configured in test layer and can also be overridden via UVM command line processor. F. UVM memory expert adapter. MEA is an UVM object and derives from the UVM_reg_adapter. In general, the verification engineer created the register adapter, which derives from the UVM underscore reg underscore adapter as well. To build the UVM register layering, the MEA is only working for the UVM MEM operation, and the bus2 reg and the leg2 bus usage model are reverse comparing with the UVM underscore reg. To make things simpler, we create a separated memory export adapter and the legacy UVM underscore leg adapter usually exists in the UVM VIP package as built-in features. G. Main features key APIs in SSMM. The typical APIs are listed in the Appendix 1. User can call such APIs in UVM sequences or components. The H. The typical use model study. To help the audience better understand this verification methodology, we try to present the details for several potential questions. How to create a SSMM. Instance initialize the user-defined MEM underscore export2 underscore CFG if the system memory segment is not unique. For example, the IP stand-alone uses the default unique memory segment and SSC needed multiple different memory segments based on system memory map definition. In the base test layer, we declare the MEM underscore export2 and the GMEM instance. It uses the config underscore MEM underscore export2 to create a built-in memory, allocation manager, and S-thread memory model. The user may set the max underscore allocate underscore side with the proper values to avoid memory allocation abuse. Figure 3 is code example to create a memory export and GMEM. How the USM SEQ works with a specific UVM slave VIP. Firstly, let's talk about the traditional use case when we verify the DT master to perform DMA traffic. We integrate the slave VIPs and enable each autoresponder feature with a built-in memory model. The slave responder will process the request, communicate memory model to save and restore data, and then simply send back the response to DUT. Figure 4. Traditional built-in memory model in UVM VIP. The VIP slave driver usually provides more comprehensive protocol features than simple slave autoresponder, so our solution is intended to use VIP slave driver with MEM underscore export and a unique slave sequence to achieve full bus protocol. The figure 5 depicts a clear picture of a workflow using USM SEQ and UVM slave VIP. Figure 5 how USM SEQ works with other slave UVM VIP. The virtual sequencer is defined UVM underscore analysis underscore expert, UVM underscore TLM underscore analysis underscore FIFO, and mailbox. The UVM underscore analysis underscore expert is connected to UVM VIP, monitors request analysis port, REQ underscore AP, and subscribes the request transition from the DUT master bus. It's also connected to the UVM underscore TLM underscore analysis underscore FIFOs and analysis underscore export and puts requested transaction into TLM underscore FIFO. So the mailbox is used as a bridge to pass data between the virtual sequencer and the unique memory slave sequence. When on-the-fly reset happens, these FIFO should be flushed automatically. The figure 6 is code example in the virtual sequencer. The background virtual sequence defined all free running subsequences in the background, such as unique memory slave sequences, interrupt service sequences, and etc. It assigned the virtual sequencer's mailbox reference to unique memory slave sequences, get the requested transaction from virtual sequencer, UVM underscore TLM underscore analysis underscore FIFO, and push in back to the local mailbox. In the fork and join underscore known block, the unique memory slave sequence is executing the VIP slave sequencer, which has reference in the virtual sequencer. In figure 8, the requested status responds to transaction different types, so it configures the mem underscore export using the mem underscore fe dot set underscore req underscore rsv underscore div underscore hdl API when the building map underscore exporting in the test layer. Figure 7. Code example of creating memory slave sequence in the background virtual sequence. The unique memory slave sequence defines a mailbox to get the requested transaction and MEM underscore expert to cooperate with the GM. It sends the request items to GMM by calling the mem underscore expert dot interwork to GMM and return the proper response depending on VIP. At last, it sends the specific response items to the UVM VIP using UVM underscore send. In the VIP, the slave driver can get the response via get underscore next underscore item and the process response items on the bus interface. To make a better trace of the response, it adds one variable named RSP underscore ID to count response number and print in the log file. Figure 8. Code example in the unique memory slave sequence. The UVM underscore env integrated all UVM VIPs, interface UVCs, IUVC, and other module UVCs, MUVC. The related analysis underscore potent analysis export are connected to the connect phase. Figure 9 is code example of a connection, the TLM underscore FIFO between VIP and a virtual sequencer. How does the memory expert adapter handle the protocol specific? The memory expert adapter is built in the base layer, and the sequence each reference is passed to the SSMM using set underscore adapter function. Figure 10 depicts the detailed memory expert adapter working flow. When the unique memory slave sequence gets the request item, the sequence will call the SSMM dot interwork to GMM function and pass down the requested response. In the interwork to GM function, it first calls the adapter burst reg to translate the burst request items into GMM underscore items, which has a few elements such as address, data, and etc. It uses the get underscore item function to get the GMM items and communicate with the GMM using the backdoor underscore item to GME function. At last, it calls the adapter's burst reg function to generate the burst response items and return. In Appendix 2, it listed the elements supported in the origin UVM underscore reg underscore items and customizes a few of them to support our solutions such as error injection. The figure 10 is a how to protocol adapter working with memory slave sequence, and the figure 11 is code example of interworking with the GMM. So the how to achieve backdoor access to the memory model, GMEM or Velo VHDL legacy memory model. The memory backdoor access is an important method. It improves the efficiency of verifying the memorized since it can access the location with a little or zero simulation time. It's usually used for initialize data buffer to prepare DMA traffic or get data from memory or for checking or prediction. In the legacy verification environment, the integrator may instance the Verilog or VHDL legacy memory model. When we adopt the system memory methodology in the legacy environment, They still use the legacy model and require vector access using SSMM. So UVM methodology provided UVM methodology. UVM provides some method for UVM_mem to support the backdoor access. User could call the add_hdr_path_slide function to set the memory location path. Then directly call the peek backdoor read and or poke backdoor write tasks. SSMM also provide the proxy APIs named the peek legacy and the poke legacy task to do the same. Users can alone also adopt the for backdoor access function, backdoor_write to gmem, and backdoor_read for gmem, backdoor_batch_read for gmem, the backdoor_bitstream_write to gmem, and backdoor_batch_write to gmem to save the restored data in gmem directory. So how to achieve the front door access using built-in UVM MEM model. When we verify the slave IP, which has internal shared memory and external memory interface, and usually adopt a master VIP to exercise random memory traffic using an SSMM memory allocated manager. SSMM provides the proxy APIs, write and read function to call the UVM_MEM memory write read functions to perform the front door access, and the legacy UVM register adapters legacy bus function, which required to implement a few code to support the memory operation, such as burst, write or read, and etc. There is no need to update to the bus to reg function for prediction, because we don't save the data in the abstract memory model derived from the UVM_MEM. In addition, the proxy APIs will call the SSMM backdoors APIs to save and restore data in GMEM as second copy. It will be very useful for data checking. And the data fabric verification is usually integrated several master VIPs on the slave port of the fabric and the slave VIPs, or memory controller with the memory models on the master port of fabric. Every master VIP is attached with a similar UVM memory expert layering. The problem is that we have multiple different physical interfaces. To address this challenge, SSMM provides the UVM_MEM_expert_CFG class for the user to define different information to create multiple maps. Each map will add proper memory segments using the add_MEM function, because each master has predefined accessible memory segments based on the associated system memory map definition. Figure 12. Front door and use model in IP level. Figure 13. Front door use model in associative level. How to support the multiple outstanding requests. To improve the performance, most of today's designs support multiple outstanding requests during the DMA traffic. However, the simple auto responder could not support it. Verification engineers may use the pending outstanding request number to create a functional coverage with the other points. User can set the outstanding request number and a timeout threshold, which ensures no simulation halt. And this feature can be disabled and enabled by calling SSMM APIs in the UVM components and sequences. Its value also can be changed on the fly. In the unique memory slave sequences, it has two concurrent threads at the beginning of the body task, and one is waiting for pending the request number till it's equal to the setting. Another is to count the time takes and break the first thread and when reaching the timeout threshold. It also records the current pending request number in the SSMM. User could call specific APIs to get it and audit with other verification points. For example, DUT assigned needs to ensure there is no pending outstanding request when a specific event or scenarios. When the outstanding request number reaches the setting, the UVM VIP should assert each ready signal until it's allowed to offset more. To support this, UVM VIP must support external ready control mechanism. Otherwise, you have to force the ready signals when the outstanding request number reaches the setting. So how to achieve out-of-order transaction completion. When implemented generic FIFOs and instancing a unique memory slave sequence, this FIFO can reorder the pending request and pop up the first request items to process. How to achieve the errors injection. Error injection, detection, and recovery are really important to verify the design robustness. Our methodology is protocol independent, so the idea is deploy the different memory exposed adapters for protocol-specific error injection requirements and coordinated SSMM. The SSMM provides several APIs to enable different error injection types and user-defined random delays in the multiple errors and etc. The user can enable and disable the error injection features during running time. The disable operation will clean all local settings, so the user should set the specific error injection before next enable operation. It executes one-time error injection by default. Here is an example of a features error injection for the AXI4 protocol. Table 2 is error injection types for AXI4 protocol. How to achieve non-post or non-post response time and legacy control. In the PCI protocol, the memory write is post operation, and means no response is needed. In this case, we should change the provided responses speed in the memory export adapter dynamically. User can enable or disable global no responses dynamically. SSMM will audit the adapter that provides response status and m_global_no_RSP bit to bit to decide if the sending back the response item or not. To mimic the real system, it requires several latency cycles before returning the response. The random latency cycles can be controlled by latency knobs, or a user set a global value by calling a set_global_RSP_latency_DLY the API dynamically. How to achieve the random burst response delay. For DMA traffic, IP usually allocated several exclusive memory regions, issues multiple burst requests to slave VIPs in return the response per each request. The first response happens between two whole responses. A whole response may contain several bits and belong to the same memory region. For example, AXI read burst response and which contains several bits, and a random delays and AXI read burst response which contains several bits. Figure 14, a code example using the memory export in the UVM sequences. How to make the use of the built-in memory allocate manager. In a real OS operation system for specific applications, it's required to allocate multiple exclusive memory regions located in random system memory segment. In the design verification world, we really have the same requirement. For example, IPDMA traffic needs to allocate reserve the initial data buffer, command table buffer, and data exchange buffer, and etc. All of them must be exclusive and can be cleaned to improve the simulation performance when they are useless. As Appendix 1 shows, the SSMM provide multiple APIs to support different memory control allocation and free requirement, one region or all of them. The free operation will delete the allocated region in the abstract memory model and also support the option to clean the related GMM buffer with X data. It provides two APIs to support only erase GMAM with all general or random data. The user can call them in sequences anytime. 3. Portable solutions across the different verification platforms. The IP UVM standalone verification platform. The IP level standalone verification platform is designed to verify a specific IP with multiple UVM VIPs. Figure 16 depicts on overall UVM IP standalone test bench. The IP RAL model, GMAM, and MEMS export built in the test layer and pass down these references through the hierarchy UVM component via UVM_configure_DB. The module UVC will get the references and assign to the module configuration object, which is shared between the UVM sequence and the component. All interface UVCs are acting in active mode and communicating with the DUT. When the IP module is vertically reused at a high level, they will be configured passive mode and only make the monitor active to spy the bus and predictor and the scoreboard for self-checking. The figure 15 is methodology adoption in UVM IP standard environment. Figure 16 is methodology adoption in IPv4 environment. IPv virtual FPGA verification platform. The API, the virtual FPGA verification platform is designed to verify IP, especially for new design and new design or big design changes in the cycle-based simulation before the real FPGA verification. Figure 16 depicts an overall IPv virtual FPGA test bench. When the FPGA verification finds a potential design bug, virtual FPGA can reproduce, review in the fixed data in this platform. Beside of the design analysis, the virtual FPGA platform has more synthesizable glue logics are involved, such as the PCIe gasket. We integrated the PCIe master and slave UVM VIP, implement the PCIe RAR layering to reuse the IP level RAR sequences. The reusable IP level module UVC is also integrated in the IPv virtual FPGA environment to achieve the IP prediction, functional checking, RAR model prediction, and functional coverage collection. IP RAR model, GMM, and MEM export are built in the IP virtual FPGA test layer, and pass down these references through the hierarchical UVM components, such as IP virtual FPGA environment and reused IP level module UVC via UVM_configuration_DB to ensure they are consistent. The IP or Mega IP UVM CW SoC verification platform. In an SoC design, the different design teams will deliver the IP or Mega IP. The integration team integrated the separated IP or the Mega IP into a bigger IPs and attached them on the data verification platform is designed to verify the separated IPs, basic functions, and connectivity in the SoC design database. It only cares about data path verification between IP and subsystem data fabric, so other unnecessary IPs will be replaced with shells and code stub. So it helps to accelerate the compile and runtime. The Mega IP looks like kind of a big IP, which integrated more IP inside. The figure 17 depicted an overall IP or Mega IP UVCCW test bench. On the data fabric, we adopt in-house or third-party UVM VIPs and implement others like UVM RAR, layering, and reused IP level modules UVC, which are similar to what the IP virtual FPGA verification platform does. IP RAR model, GMEM, and MEM both are built in a UVM CW test layer and pass down the references through the hierarchical UVM component using UVM underscore config underscore DB. The figure 17 methodology adoption in IP UVM CW SoC environment. D. SoC full chip UVM and verification environment. When all of the IP are ready and integrated into SoC-based database, IP UVM raw sequence library and the legacy double plus test can be reused to verify the function of SoC. To speed up the simulation, we use the UVM VIPs to replace the CPU complex design, which actually presented the shell. In the SoC verification, it adopted the real memory controller with a available VHDL or VIP memory model. We only need to capture the write request and fill data into GMEM. The TLM2 APIs are designed to connect legacy C++ test cases with a UVM master VIP. We have lots of legacy C++ tests which adopt the legacy C++ memory model. In order to align with the methodology, we created several DPIs to make communication between C++ and the UVM memory models. The UVM slave VIPs monitors spider data bus around the fabric and broadcast the write request information to unique memory slave sequence, and then the user MEM export to write data into GMEM at the same time. The data will be written to C++ memory model via DPIs, and this way, the data will be consistent between different memory models. All IPS module UVCs are reused at SoC level to do the self-checking, IP functional coverage collection, and RAR model update. IP RAR model, GMEM, and MEM export are built in UVM test layer and pass down these references through the hierarchical UVM component using UVM underscore configure underscore DB. The debug. Figure 18 is methodology adoption in SoC full chip environment. Section 4 is debug. Debug is already painful for most of the verification engineers who usually take more than 50% time on the debugging, such as the design verification environment and test cases. Our solution offers several mechanisms to help understand the information of the memory allocation data in GMEM and error injection, outstanding request, latency, and so on. And the verification environment, MEM underscore export, reference could be got via UVM underscore config underscore DB in both UVM component and sequences. The user can call the specific debug APIs to get a proper information beside the API capabilities. Necessary debug-related information with different purposes is developed. For example, UVM underscore low gives the debug messages that indicate a major event. The UVM underscore high give the debug messages or methodology implementation, and developer could use them to fix bugs. The user could set the proper verbosity of the get a different level debug information via UVM command processor. The following table presents an example of a dump function to show all allocated memory regions. Okay, no caption. In section 5, success stories. Our portable and reusable UVM shared system memory model verification methodology has been across the numerous UVM projects in our group for more than 3 years. Typically, we can see a project obtaining an approximated 96% effort reduction compared with creating a memory model methodology from scratch and reusing during adopting the UVM VIPs and different protocols across different verification platforms, as we can see in the following table. When we verify the two IPs and which adopt the same protocol or UVM VIPs, the verification effort in the second IPs is significantly reduced with the benefit from the portable and reusable capability of our solution. Furthermore, the experienced engineers can easily understand how to integrate and use this methodology by reading details user guide and eventually reduce more time in the last project. With the help of the flexible debug capability, verification engineers could find bugs in our comparing to get more than 1 day without such help. The outside the box, the verification engineers keep raising more interesting requirements to inspire us to enhance this solution to accelerate project execution. This box, this table. The two other more interesting verification challenges we need to continue to develop after this methodology. We are concurrently planning to include the following to improve the extension later. To refine all error injection using the extension UVM_ object declared in the UVM_ leg_ item to support the user-defined backdoor access, to support error injection with random in multiple error types at a time. Even better debug aiding mechanisms. Support more potential bug protocol UVM_VIPs. Support the DDR4 abstract model. Conclusion. Section 6's conclusion. In this paper, we present a portable and reusable UVM shared system memory model verification methodology and its typical use model. Lots of friendly API synthesis and make people easily deploy the verification requirements. The flexible debug information shows a clear picture of what engineers want to see to reduce the debug time. The exporter adapter libraries provide a quick connection to the different bus protocols and a bus protocol independent unique memory slave or a server sequence bridges the gap the adoption of different protocol VIPs. Based on our numerous successful UVM project experience, this methodology can be a portable and reusable across multiple verification platforms. UVM IP or Mega IP stand alone the UVM CW virtual FPGA and as a full chip to dramatically reduce verification effort. So the current is not the end and is it keeping the evolving. And a reference. Okay. Appendix. Okay. Today I read this paper. This paper. Okay. This paper. The art of portable, use and reusable UVM shared system memory model verification methodology across multiple verification platforms. Thank you for your time and thank you for see you next time.